Did I just show you guys? Professor would zero grandson his job provides so that he actually says that should yeah, so these are I don't mind. It's okay, I really
You didn't mention it, so I assume
I said I'd seen it. Did Ricky say it was kind of slacking on you?
No.
Yeah, that
Ricky's
was
slacking in your group?
straight off. I want to say something about that. Well, you're also in the engineering chat. Ricky and I are kind of.
Hey, I was not saying that.
So
Oh, it's gonna be.
pretty good, though. You sound kind of sick.
So pretty much. Sure. No, I didn't tell him, I honored my services.
Yeah, everybody from that system you like to teach class 5 pretty well.
Are you in a class that's like this half of the lab is just
Oh, you've heard?
I've heard.
Yeah, oh boy, that's fine. That's but anyways, he was the originally was so he was like, oh.
Hey Charles, how's it going? Yep, what's up?
so I'm doing an assignment. I don't know whether the mistake happened.
You want to know the best
when it
words
was
he gave
mechanical or whether it was when I turned stuff into beams.
Yep.
But I remember connecting the road. You said we had to the road connects to the beam, right?
Yep.
So it's supposed to be like this. However, I ran my simulation
and he was like, all right, I'll give you the extension.
it ended up like this.
It looked like the
No, you
beams
just
were
said any reason. I'm like,
In-
no, what is
Into the road, like halfway through.
Oh, okay, that's if it's just visual, it's okay. Are you seeing kind of the deformation kind of maximize down here and then kind of go like
No, I
that?
just generated the mesh. I haven't put any forces on it yet.
Okay, yeah, if it's just like this, it's just a visual thing. So I would keep going and apply the forces. And so what you should see from the deformation is that, you know, it's I'm assuming that you put kind of a vertical force down like this. And so if you put kind of a pressure force on top, then the deformation will kind of have this kind of like jump rope looking thing. So it'll come down in between the beams, but then it should come back up like the other beams, come down like that, come down like that, come down like that. All right, and so that's kind of your real test, but because shells and beams, every version of this shows a bit differently, and so the one I have kind of shows them as kind of a thin sheet, just lines. But I know that there's some answers out there that actually put some thicknesses on these, just to be super confusing. So yeah, so don't worry about any kind of visual stuff. It's just how it renders it. But then the real tell is when it runs.
All right. Like you said, it should be the fixed deformation, like a sort of like parabolas.
I think I have images of the deformation. So you should try to get something similar. All right. Yep. Okay, for problem 5. You don't have to, and so you may not get convergence because it's kind of a little bit different for everyone. Depends on your boundary conditions too. So if you're doing that, just show me the plot. That's fine. And in terms of the bridge itself, it's actually kind of a teeny tiny bridge. It's actually like a toy. It's actually like a toy bridge, and so you can kind of make up your own story for it. Okay, yeah, just show me the scatter plot. That's enough for that. That's good. It's good that you're thinking about the some real numbers for these. I don't know. I saw someone mention it on the Discord, but I haven't heard anything.
Okay.
You haven't-
I have a question on the limit.
Yep.
Which ones are the constraints? Is that the big one? Or I'm sorry, not the constraints. I forgot what it was called.
Oh, the target and the contact.
The target and the contact.
Yeah, so the target's the bigger one, the contact is the smaller one.
Target is the bigger one,
Yeah.
contact, and then the contact you do multiple at a time.
You can do multiple time for both, but usually for the contact, you do multiple.
And then we do it on both sides.
Yes, yeah.
Got it. Okay, awesome. Thank you.
Mhm.
Probably on the last one. Yeah.
Ah, I see. Oh, I mean, we could use some rain, so thunderstorm wouldn't be a bad idea. All right, it's 5:30. Let's go ahead and get started for today. Okay. A question for midterm template. I'm using your lab template. That's fine. I mean, as long as you have the same sections, you can use whatever font or template that you want. I just want to make sure you have the same sections. Okay, so let's go ahead and get started. Right. So how's everyone doing today? Good. Right. Okay, so today in finite elements, we're going to be kind of doing a shift, and so we're going to take a departure from where we've been doing. Okay? So kind of up to this point, we've been doing like pretty hardcore ANSYS, and so we're doing just ANSYS activity after activity, and we've been in the lectures we've been learning a lot of I would say practical knowledge in terms of using ANSYS, and so we're going to take a break from that, and so because I know that there's the activity that's out there. And then there's the midterm project that's out there as well. And so, we're going to have kind of a breather on the ANSYS stuff for a while. Okay. And for the next few weeks, we're going to talk about finite element theory. Okay. And so underneath ANSYS and within, the programming and the code, there's some actually really interesting mathematical theory behind it. Okay. And actually, if you tell most people that you took a finite element class in college, there's going to be some expectation that some theory. So, that's from the companies, or if you plan to pursue this in grad school too. So, this is kind of me satisfying that obligation just to make sure that you have some idea of the theory. It's not going to be enough to write. I'd say write your own code. I think we kind of need to devote a much larger portion of the class for that. But I think it's important just to know kind of what's going on under the hood and what the elements are doing, how they interact, and kind of what it looks like mathematically under the hood, just so you kind of have a better appreciation for what ANSYS is doing. Okay, and so we'll be doing theory for the next few weeks. There is going to be a homework assignment for this, but we're not really going to talk about that until after the midterm project, because I want you to mostly focus on that. Okay, and that's what we're going to do. Okay. So I have the set of lecture notes for this week. It's only 8 pages long. And so, what I'm hoping for is that it's not going to take the entirety of both lectures this week. And so what I'm hoping for on Thursday is that, if we do finish early on Thursday, we can spend some extra time working on the activity. Because I know as a group, we didn't get as far as I wanted to on the activity in terms of, getting the simulation results. And so if you're still working on it on Thursday, then we can spend some time, hopefully in the later half of the class on Thursday, working on that together. Okay. Because I know activity 4 is kind of a long. So, I want to make sure I give you guys enough support in doing that. So you can kind of look forward to that on Thursday. Okay. All right. And so that's all my announcements. And so are there any questions I can answer before we get rolling today? Okay. All right. So let's go and get started. Start into our journey for finite element theory. And so it's going to start with something called the direct stiffness method. Okay. All right. So let me start today just by kind of reminding you that finite elements, at its core, is just a way for you to solve partial differential equations or any differential equations. Okay. Okay. And it does this in kind of a very specific way. And so the way that FEA works is that it takes this very complicated differential equation, and then it aims to turn this into an algebra problem, basically. Okay. And so at its core, FEA it doesn't actually solve the problem for you. All it really does is it takes one problem and just puts it in a different form, okay? And so, that first statement's a little bit misleading. So, finite elements it doesn't really give you a solution to a differential equation. It just puts it in a much easier form to deal with, okay? And so finite elements is just the methodology to go from differential equation to algebra problem. And then once you get to an algebra problem, you can just solve the algebra problem, okay? Because generally it's a lot easier to solve an algebra problem, especially for a computer, than differential equations, okay? And so visually, look something like this. So you're going to start with a differential equation, okay? And then you're going to go to algebra problem. And in between, this is FEA. Okay. And then from the algebra problem, you just solve the algebra problem. I make that step sound simple because algebra is it's easier than differential equations, but it can still be really hard. And you'll probably over the next couple of weeks, we'll be doing the theory and you'll be looking at the algebra problems that we're getting, and you're going to look at me and say, that's not easier, that's harder, And so, algebra is not necessarily easier, at least for a human, but it is a lot easier for a computer. Okay. And so if you can take a differential equation, turn it into an algebra problem, then the computer is much better equipped to do that. Okay. And so with that said, this step right here, this FEA step of turning a differential equation into an algebra problem, there's lots of different ways to do this. And so like you hear very commonly, there's lots of different ways to skin the cat. And so even though we talk about FEAs as if it's kind of one thing, there's actually lots of different ways that you can perform FEA. Okay, so there's lots of different FEA implementations out there. Okay. And so the reason I'm bringing that up is that this direct stiffness method that I'm going to be teaching you is not really all that similar to what ANSYS is doing. And so the direct stiffness method is just one way to perform FEA. Okay, it's not very practical for real life problems just because it's very simplified. But the reason I teach it is because that for traditionally it's kind of the first method that most people learn when they're learning FEA theory, and so it's a lot simpler to digest. But even in its simplicity, it still gives you a lot of really good insights to how the finite element process works on a theoretical and kind of on an algorithm level. Okay. And in fact, I would argue that most of the direct stiffness method is actually the same as a normal FEA, like what ANSYS is doing. There's just one kind of key step that's different. And so of course, that key step is that's a lot of FEA algorithms kind of built on that step. And so it's a really important step, but all the other steps are mostly the same. Okay. And so, I think I've done enough teasing. And so let's talk about what the stiffness direct stiffness method is by talking about something called the stiffness matrix. Okay. And so to introduce the stiffness matrix, I'm going to kind of bring up an old friend. Hopefully it's an old friend. And that's going to be a simple spring and Hooke's law. So let's consider a simple spring. And so here we have kind of a fixed wall here. Okay. And we have a spring attached to the wall, because why not? Okay. Let's say that we're going to pull on the spring with the force F. Okay. All right, and so we know the spring has a spring constant K. Okay. And so if you recall, the units for K is newtons per meter. Okay, at least in SI. Okay, so that's the spring constant. So that tells us how strong the spring is. Okay. The spring also has a default length. And so the default length for the spring is L. But, you know, when we apply the force F on it, the spring is going to extend. Okay. And so this D here, this is the amount that the spring is stretching in response to the applied force. Okay. Okay. Right, and so from this kind of simple spring right here, we can form Hooke's law, right? And so Hooke's law basically gives us the mathematical relationship between the amount of force that we're applying on the spring, its deformation, and its spring constant. Okay? And so Hooke's law basically says force F that we apply on the spring. And I'm writing this obnoxiously large so that I can draw a lot of subnotes, but you don't have to draw it as obnoxiously large as me. Okay. And so the force F is equal to the spring constant K multiplied by the deformation. Okay. So hopefully that's a a formula that you're familiar with. Okay? It's a very simple formula, right? It's only 3 terms, and we just have a simple multiplication. Right? But believe it or not, this simple formula here kind of forms the basis for how we form FEA problems. Okay, and I'm going to show you kind of what that looks like. So first thing I'm going to do is I'm going to go term by term here and kind of talk a bit more in depth about what that term represents. First of all, what it represents for the spring, but also how we can kind of generalize that kind of relationship to any other system. Okay. Right. So let's start with the force F here. Okay. And so this force F is what I would consider an external force. And so it's some kind of external entity that is acting on the spring that's causing it to react. Okay. Okay. Because that force F is not produced by the spring itself. And so it's either some external device, external person, external thing. Okay. And so that F has to be from external. Okay. And what you'll notice is that the F is kind of sitting on one side of the equation all by itself. Okay. And so we have the equal sign. And so everything else in the system is on the right, but the F is kind of chilling by itself on the left. Okay. And so that's going to be an important point that we'll come back to a bit later too. Right, next we have K. And so of course, K here, this is the spring constant for the spring. And the spring constant is something that I would characterize as a material property or material constant of the subject. Okay. And so we know that if we're looking at a spring, right, the higher the spring constant is, the more it's going to resist deformation, right? And so a spring with a very high spring constant is, going to resist it a lot. And then springs with the low spring constant will, just kind of be like a slinky, basically, okay? And so in other words, the value of this property basically defines how the system is going to react to the external factors, okay? And then finally, we have D. And so D, of course, this is the amount that the spring is deforming, okay? Another way that we can view this D here, if we kind of extrapolate and kind of look kind of more broadly, is this is the system's response to the external force, right? And so if the spring constant or the material property there that determines how the system will react, the D there is the actual response. Because anytime you have any kind of external effect on a system, then it's going to react in a certain way. And so the D there kind of characterizes the response. Okay. Right. And so, even though we have a simple equation here, there's kind of a lot of, really rich information that we can pull from it. Okay. And if you notice, a lot of how I've been describing these terms are kind of consistent with how we've been describing a lot of our finite element stuff, right? And so, for instance, the force F here, we know that that's some kind of external effect or some kind of external force, right? And so, what's the concept of an ANS that we've been looking at that acts as an external force? Right? These are like our boundary conditions. Next, let's look at K. And so I said K there is, it's already in the name. And so I already said it's like a material property or material constant, right? And so we know from our ANSYS activities that constants like the Young's modulus, like the density, those are going to affect the response. Okay? And so these are just like the material properties. Okay. And another thing I'm going to throw in here, just because it's going to be relevant to our discussion, is this is the geometry as well. Okay. And so a spring, we don't have any geometrical properties of a spring, but for other FEA, the geometry is going to be there as well. And so the size, the area, the lengths, and stuff like that of your system, it's going to have basically the same effect as K. Okay. Right. And then the response D, this is like our solution, right? And so when we apply our mesh, we apply our boundary conditions on our finite element system, and we hit solve in ANSYS, we get things like the deformation, we get things like the stress, okay? And so that D right there is like our solution, okay? And so, again, we have a very simple, very, very simple Hooke's law equation here, 3 terms, but, there's so many parallels to, how we kind of understand finite elements. And this system here is actually going to be the basis of, of our theory, okay? In particular, we're going to focus on this K right here, okay? And so that K, one way that you can think of it is that that's kind of like the stiffness constant of the spring. But then when you kind of extrapolate this and you kind of apply it to, say a finite element mesh with tons of different nodes, instead of a constant, what you're going to have instead is a matrix. Okay. And so that's going to be the focus on of a lot of our theory. It's what the stiffness matrix is, what it represents, and how do we actually use this in computations. Okay. All right. And so as we go through the theory over the next couple of weeks, we'll see a lot of different expressions for stiffness matrices for different types of structures. And one thing that you'll see as a constant is that the stiffness matrix always contains things like material and geometric properties of the system. Okay. All right. And this structure here is not just limited to structural mechanics as well. And so if you look at FEA for like heat transfer, look at FEA for fluids, you have the exact same structure. So you have external effects, you have important material parameters, and you have the response, except the specific values of these are going to change. And so let's say for heat transfer, the response for that will be temperature, and the material constant for that will be things like thermal conductivity, thermal diffusivity, things like that. Okay. But the same kind of idea stands, where if you have the external force, that's going to equal to material constants multiplied by the response. Okay. And this basic structure is used for basically all of finite elements. All right, any questions on this? All right, and so let's take the structure here and then let's actually apply it to the spring, and let's see if we can get the stiffness matrix for a spring. Okay. All right, and so a matrix implies if K there's a matrix, then in order for that relationship to hold, that means the F and the D terms have to be vectors. Okay? Okay. And so particularly, we're going to look at a spring, and we're going to consider the two edges of the spring. Okay. And so we're going to consider one side like this, F1, F2. Okay. And so we're going to have node 1 on the left, node 2 on the right. Okay. And then in response, we're going to look at their corresponding deformation. So we have D1, D2. Okay. And so what we want is we want an algebraic relationship that relates F1 and F2 to D1 and D2. Okay. And of course, the spring has a spring constant of K. Okay. And so using that same structure that we had above, and so if we kind of isolate the forces on the left-hand side, so we have F1, F2 as a vector, okay? And this is going to be related to D1, D2, okay, which is also a vector. And then in order to make this kind of algebraically sound, our stiffness matrix here needs to be 2 by 2. And so we need to have K11, K12, K21, K22. Okay. And so this is kind of a very simple kind of stiffness matrix or stiffness system for a spring. Okay. And what we're aiming for is we want to find the values of this stiffness matrix right here. Okay, so let's go ahead and begin. And so first thing we're going to assume here is just for simplicity's sake, let's assume that our spring is in static equilibrium. And so that means if we have our spring just like this, static equilibrium means that if we sum up all the forces on the spring, then it's going to equal to 0. Okay. And so that means if we apply a tensile force T on the right on node 2, that means in order to get static equilibrium, we need to apply an equal and opposite force on the other side of the spring, which is side 1. Okay. All right. And so, of course, you know, what we expect is that if we take a spring and we kind of pull on it from both sides, the spring is going to lengthen. Okay? And so the way that we can represent that is that we can say that node 2 displaced by an amount d2 and node 1 is going to displace by an amount d1. Okay. So d1, d2 is how much the spring is deforming in response to the tensile force at the 2 nodes of the spring. Okay. Okay, so let's form Hooke's law for the spring. And so Hooke's law basically says that the force that we apply on the spring, which is T, is equal to the spring constant multiplied by its deformation. Okay, and so its deformation here is going to be its change in length. Delta right here is going to be the change in length spring. So that's just kind of straight up Hooke's law just on its own. First thing I'm going to do is I'm going to take that term delta right there and then put it in terms of the nodal displacements, okay? Because we don't have delta in our figure, but we do have our D1 and D2, okay? And so I'm going to replace this D1 and D2. Okay? And so we have T, which is equal to K. Okay? One way that we can compute the change in length is we just take the difference between D1 and D2, okay? Because we know D2 is deforming to the right, or node 2 is deforming to the right, node 1 is deforming to the left. And so if we take the difference in between those deformations, then that's going to be the change in length. So this is going to be K times D2 minus D1. Okay. And so we have this relationship here where the tensile force on the spring has to equal to the spring constant times D2 minus D1. Okay. All right, so now that we have this expression that relates the tension to D1, D2, let's relate the tension T to F1, F2. Okay. And by F1, F2, what I mean are the external forces that are being applied on node 1, node 2, okay? And so if we go back to kind of our first figure here, okay, we can see that F1 is acting on node 1 pointing to the right, and F2 is acting on node 2 pointing to the right as well. Okay. If we compare this figure here compared to this figure right here, okay, we have tensile forces T acting on nodes 1 and 2. We can make a relationship between F1, F2, and T. Okay. In particular, we have this relationship. We have F1 is equal to minus T. Okay. Right, because at node 1 we have the tensile force pointing to the left, and so that's in the negative direction. Okay, so we can say that F1 is equal to minus T, and F2 here is going to equal to positive T, because on node 2 we have the tensile force T pointing to the right, and so that's going to be a force in the positive direction. Okay. Okay, and so the next step that we can do is we can take these expressions and substitute for T. Okay. And so we know that F1 is minus T, so we can say that F1 is equal to minus K D2 minus D1, and F2 is equal just to T straight up, and so that's equal to K times D2 minus D1. Just for simplicity, just for kind of simplicity's sake, I'm going to distribute the negative for F1. And so it's going to be K times D1 minus D2. Okay. And so in the end, we have two equations here. Okay. And so we have F1 is equal to K D1 minus D2. Okay. And then we have F2 is equal to K D2 minus D1. Okay. So these two equations are significant because remember what we were looking for when we first started out. Okay? And so when we first started this section, we wanted basically a system of equations that related F1 and F2 to D1, D2. Okay. And look what we have here. We have two equations and they provide the relationships exactly as we want. So we have F1 is equal to K times D1 minus D2. And then we have F2 is equal to K times D2 minus D1. Okay. We have two equations that kind of form this relationship for us. Okay. And so the last step that I can do here is I can put this in matrix form. Okay. And so in other words, I'm going to form a vector here. So we have F1, F2. Okay. This is equal to a matrix multiplied by D1, D2 vector. And the last thing we need to do here is just fill in the entries of that matrix based on the two equations that we have above. And so if we look at the two equations, we know that the coefficient for this part is going to be a positive K. The coefficient in the upper right is going to be minus K. And the bottom left is going to be a minus K. And then the bottom right is going to be a positive K. And so what we have here is this is the stiffness system for a simple spring. In particular, I'm going to pull out this guy right here. And so what we have here is K, a matrix of K minus K minus K, K. And so what we call this right here is this is the element stiffness matrix for a spring element. So anytime that we have a spring, we can relate the external forces acting on the spring to its to the nodal deformations using this matrix right here. Okay. All right, and so, anytime that you have an element, and I use that term very deliberately, and so an element here is very analogous to an element that you have in like ANSYS or any FEA. Every element in every kind of mesh is going to have an element stiffness matrix associated with it. Okay? And so this is probably the simplest element stiffness matrix known to man. And so you can't really get much simpler than this. But this is going to be our building block so that we can kind of, first of all, highlight, what else we need to do in the finite element method, but also kind of illustrate the fact that, any kind of element, whether it be a very simple spring or a very complicated, quadratic hexahedron in ANSYS, there's an element stiffness matrix underneath that consists of both its material and geometric properties that's going to be used in the FEA analysis. All right, any questions on this? All right, and so we've looked at kind of one element here, and the element stiffness matrix for that, but kind of the real power of FEA and just this methodology in general is for multiple elements. Okay, so let's see how we actually deal with kind of a multi-element system. And so, I don't have it listed as an example, but this is basically going to be a long example. Okay. And so let's consider two springs that are attached in series. So we don't have to make any assumptions on the springs themselves. And so we can assume that they have different spring constants. And so we can say that the first spring has a constant Ka and the second spring has a spring constant Kb. Okay. We can label the nodes. And so in between the springs, we're going to have the nodes of our system. And so going from left to right, we have node 1 and then node 2 and node 3. Okay. And then of course, at each of the nodes, we can say that we can compute the deformations of those nodes. Okay, so the way that we're going to track the system and we're going to solve it is by computing the deformations at each of those nodes. Okay, so D1, T2, and T3. Acting on this entire system is going to be an external force F. Okay, so that's going to be our kind of like our boundary condition. Okay, so you'll see how that F is going to be factored into the equation later on. And so what we want to do for this system is compute. We want to compute all the nodal deformations in the system. So D1, D2, and D3. So you might, and so I've shown this problem a couple of years now, and some people have said that they've learned how to do this in a different way in another class, and so that's great. I'm not here to trash on anyone's teaching, okay, only my own. And so what I'm going to show you here is just the finite element way to do this, okay, and it's going to utilize basically everything we've talked about today up to this point. And so we're going to utilize element stiffness matrices, and so you're going to see we're going to form them for both element A, element B. And then we're going to see how we can actually combine them. Okay. All right, and so the first step to solving a multi-element system like this is to form the element stiffness matrices for all the elements in the system. Okay. Here we only have two elements, and so we only have elements A and B, and so we're just going to have two element stiffness matrices. Okay? And so let's start with element A. And so element A stiffness matrix is going to be, we're going to follow the exact same format as up here. And so since the stiffness constant for element A is Ka, we're going to have a Ka minus Ka minus Ka and Ka. Okay. And then for B, the element stiffness matrix is going to be Kb minus Kb minus Kb and Kb. Okay. Of course, if you had numbers for this, you can plug them in, but we don't have numbers, and so we're just going to leave it in its symbolic form. Okay. All right, I'm going to do one more step here, and that's to identify which nodes each of these elements are attached to. Because if you notice, element A is connected to nodes 1 and 2, whereas element B is connected to nodes 2 and 3. Okay, and so that's actually going to be important information, especially in the next step. And so we want to make sure that we identify that. And so the way that we're going to do that is we're going to make it just part of the system. Okay, so for the element stiffness matrix for element A, we can say that it's acting on nodes 1 and 2 by saying F1, F2 is equal to Ka minus Ka minus Ka, Ka times D1, D2. And then for element B, it's going to be acting on nodes 2 and 3. So we have F2, F3 is equal to the element stiffness matrix times D2, D3. Okay. All right. So that's an important step. So that's why I kind of highlighted it, because I think kind of when you're first starting out, I think people are so concentrated on just computing the element stiffness matrices, they forget to actually identify which nodes that they're acting on. So you want to make sure that you do that here. All right. And so once you've computed the element stiffness matrices for every element, the next step is what I call assembly. Okay. And so this step kind of is in general called assembly, because what we have right now is we have two we have two kind of linear systems. And so we have a linear system for element A, a linear system for element B. Right now, it's not really that helpful because we can't actually use that to solve for a solution. Okay? And so to actually get a solution from this, we need to get a single linear system. And so this single linear system is going to combine all of the forces and the displacements for all the nodes. Okay? And so for this spring system here, we have three nodes. Okay. And so our I call it the global linear system. And so the global linear system will have three rows. And so we have F1, F2, F3. We're going to have a large stiffness matrix here. And then we have the nodal displacements D1, D2, and D3. All right. Of course, the big gaping gap right there is it's what's happening, in between. And so what we're going to do is that inside this this gap right here, which you can see here is a 3x3 matrix. Okay. What we're going to do is we're going to insert all of the element stiffness matrices into this global system. Okay. And I emphasize their proper locations because, if you look at the element stiffness matrices for elements A and B, we can see that they're only 2x2 matrices. Okay? So of course, they're not going to take up the entire 3x3 space. And so the key here is going to be to make sure that you put the element stiffness matrices in its proper place. Okay. Any questions on this so far? Okay. All right. And so how do we do this? And so how do we put the element stiffness matrices in the right locations? And so I'm gonna make an additional change here to kind of help with that. And so we've already labeled the rows. And so we know that the first row is with D1, the second row is D2, the third row is D3. I'm going to label the columns as well. And so our first column here is going to be D1. Our second column here is going to be D2. And our third column here is going to be D3. Okay. So I'm going to do the same thing for our element systems. And so for element systems, I'm going to use red, just because I'm kind of coming back here. Okay. And so for element systems, they also have rows, columns associated with them too. And so for the element stiffness matrix for element A, the first column is D1, the second column is D2, and then for element B, we have D2 and D3. And so when you label the columns like this, the assembly becomes fairly straightforward. So all we're basically doing is matching the exact same coordinates for D1, D2, and D3 for each of the element stiffness matrices. Okay. So let's see what that looks like. And so let me start with element A. And so you know that element A acts on nodes 1 and 2. Okay. And so that's going to be on the D1, D2 row. and the D1, D2 column. Okay. So it's going to look like this. And so inside that dotted box right there, that's going to be the entries of element A. And so let's go ahead and put that in. And so element A, we know its element stiffness matrix is Ka minus Ka minus Ka and Ka. Okay. Next, we have element B. Element B we know is nodes 2 and 3. And so in the global system, that means it's going to be on the D2 row, D2 column, and D3 row and D3 column. Okay. And so if we draw a dotted box, it looks something like this. So we have minus KB, minus KB, KB. Right. And so of course, we have an overlap. And so we have an overlap on that D2 spot. And so you might be wondering, what happens when you have overlapping element stiffness matrices? Well, it's very simple. And so all you do is just add whatever overlaps. Okay. And so in this case, we have just one overlap on node 2. And so in that 2, 2 slot right there, we're going to have Ka plus Kb. And for anything that's not claimed, and so anything that's not within a box, we're just going to put 0. And so we're going to have a 0 here and a 0 there. So let me scroll up a little bit here. Right, and so you can see we've made some good progress. And so we started with our element stiffness matrices. We've assembled them into this global system. And this is kind of where we're at. Remember what I mentioned at the beginning. And so what I said at the beginning was that FEA was a way to take a differential equation and turn it into an algebra problem. Okay. Obviously, we're not starting with the differential equation here. That would be kind of a whole nother class. But you can see here that we have an algebra problem. Right? And so we have, it's in matrix form, of course, but we have a system of 3 equations. F1, F2, F3, and 3 unknowns, which is D1, D2, D3. Okay. And so we have exactly the number of equations that we need to solve for the unknowns. Okay? So 3 equations, 3 unknowns. Right. And so we've kind of accomplished what we set out to do, which is to get an algebra problem out of this physical problem. Any questions on what we've done so far? Okay. All right, so this is looking good. And so, you might say that we've accomplished our goal. And so we've gotten our algebra problem from the physical one. Unfortunately, this algebra problem is not solvable. And so if you look at this matrix, if I draw a line kind of through this matrix like that, you'll see that this matrix is symmetric, on the top side of the diagonal versus the bottom side. And one thing that we know about symmetric matrices is that we can't solve them algebraically. And so this system right here is not quite ready to solve. And so before we can actually solve for its solution, we need to apply boundary conditions. Okay. And so, like I said, remember, boundary conditions are basically all of the external effects that are acting on our system that are affecting the solution. Okay. If we look at the figure for this solution or for this problem here, okay, we actually have 2 external effects. Okay. The most obvious one is, of course, the one on the right. And so on the right here, you can see we have an external force. Right? Another way that we can say this is that this is a load. Okay. So to kind of keep our terminology consistent with when we talk about boundary conditions and ANSYS. Okay. And so that's going to be our load type boundary condition. And then our other boundary condition is actually on the left. Okay. And so our other external effect here is a wall. And so what the wall is going to do is that it's going to constrain our system. Okay. And so this right here is our constraint. So we have one load and one constraint. Okay. And so it looks like just a very typical finite element problem. And so the next step is to, actually see how to mathematically represent this load and this constraint into the boundary conditions. Okay. So let me first start by saying that mathematically, loads and constraints are handled differently in the global system. Okay. And so, kind of exactly how we think about them differently in ANSYS, they actually are handled very differently mathematically. Okay, so we're going to talk about how to handle load type constraints. We'll do that second. First, we're going to learn how to handle constraint type constraints, constraint type boundary conditions, and then load type boundary conditions. Oh, I need to sleep more. Okay. And so let's look at constraints first. What do we know about constraints? And so think back to our boundary condition lecture that we talked about a few weeks ago, right? What we know about constraints is that they directly specify the solution variables at their location. Okay? And so to see how this is applied here, we have to ask ourselves, what's the solution variable, right? So that's kind of the key. And so the solution variable for our spring system is going to be the displacement. Okay. Okay. And so the variable that we're using to define displacement is d. Okay. And so that means that whenever we have a constraint, the displacement is going to be directly specified. Okay. And so let me go back. Let me just scroll up to the figure up here again. Okay. What we can see from this figure is that node 1 is directly attached to the wall. Okay. And so the constraint is going to act on D1. Okay. Okay. In other words, we're going to directly specify what the displacement should be at D1. Okay. And so the simplest way that we can do this is we can just make an equation. Okay. We can say that D1 is equal to something. Okay. In particular, and this is not always the case, but it is the case most of the time. What we have here is a fixed constraint or a fixed support. Okay. And what we know for a fixed support is that the displacement or the deformation at the fixed support is going to be 0. And so mathematically, we can represent that as D1 is equal to 0. Right, so very, very straightforward, right? And so for constraints, we just set the displacement or the relative displacement equal to whatever they need to be. Okay. I'm going to take this very simple equation and make it weird. Okay. So let me do this. And so the first equation there, D1 is equal to 0. What I can say here is that this is equivalent to D1 plus 0 times D2 plus 0 times D3 is equal to 0. Okay. You might be asking why I'm doing this, because normally when you multiply something by 0, it just goes away, right? So 0 times something just goes away, which is why we have that equation above. Okay. But the reason I'm doing this is so that we can fit this into our global linear system. Okay. And so I'm gonna extract this even more. And so let me go ahead and extract the coefficients. And so we put this in kind of, well, in this case, it's vector form. We don't have quite a matrix yet. And so if I extract the coefficients from this, we can say that this equation is equivalent to the vector 1, 0, 0, a row vector, multiplied by a column vector, D1, D2, D3, and that is equal to 0. Okay. And so if you perform the matrix multiplication or the vector multiplication here, you'll see that this relationship is, is legit. So hopefully you can see, the reason I'm doing this. And so the reason I'm doing this is so that, we can fit this in to our system here. Okay. In particular, what we're going to do is we're going to take this equation and we're going to replace one of the rows in the global linear system. Okay. So let me show you what I mean. So let me go ahead and draw the global linear system again. So we have F1, F2, F3. Okay. And then the stiffness matrix here, you have Ka minus Ka, 0, minus Ka, Ka plus Kb, minus Kb, 0, minus Kb and Kb. Then D1, D2, D3. Okay. All I did was I just repeated the global linear system that we had above. Okay. All right. And so, what we can do is we can replace one entire row here with the system that we had above. Okay. In particular, since this constraint is acting on row 1, or excuse me, on node 1, let's replace the row 1 of this linear system with that constraint equation. Okay. edit again, node 1. Okay. All right, so row 1 is this row right here. I guess more specifically, it's just this row right here. Okay. And so let's replace this row with our constraint. Okay. And so our constraint, we can see that in the matrix portion here is going to be 1, 0, 0. Okay. And then on the right-hand side of the equation, we have a 0. And so for constraint type boundary conditions, what you're going to be doing is you're actually going to be modifying both the forcing vector as well as the stiffness matrix. Okay. Okay. And so for that reason, constraint type boundary conditions are actually more difficult to apply mathematically. Okay. All right, any questions on this so far? Okay. All right, so that's constraints. And so now let's do the loads. Okay. So load type boundary conditions by comparison are a lot easier because the load types are usually things like forces and pressures. And so the way that you apply those is you just kind of stick them into the forcing vector. Okay. Okay. In particular, for this example, in this example here, we have a force of F being applied on node 3. And so this tells us that F3 is going to be equal to F. Okay. And so if we go to our row 3 here, okay, we can see here that we have F3 kind of sitting there by itself in the third row. Okay. And so to apply the load type boundary condition, all we have to do is just replace F3 with big F. Okay. That's all we have to do. And the last thing that we'll do is we note from our diagram here that we have no load applied on node 2, and we have no constraint there either. And so mathematically what we say is that the external force on node 2, little f2, is going to be equal to 0. Okay. And so we can put a 0 there as well. right, and so what we've done in this step is we've taken our global linear system, the one that we've assembled before, and we've applied boundary conditions. Okay? And so the benefit for this now is that if you look at our matrix here, okay, it's no longer symmetric. And so this matrix here can actually be solved. And so, now we actually have an algebra problem that we can actually solve. Okay, we have 3 equations, 3 unknowns, a non-symmetric system. Hey man, we're good. And so, we're able to solve this. Okay? And so this is the part where you look at this and say, just do the algebra, bro. And so, algebra, of course, is a lot harder than that. And so, if I told you to solve this, you would probably be angry with me. It's not the hardest one. So it's, it's 3 equations, but we're gonna look at systems in the coming weeks that are like 12 by 12 or like 20 by 20. And so, 12 equations, 12 unknowns, 20 equations, 20 unknowns. For a computer, that's actually a piece of cake. But if you try to do it by hand, you're probably gonna want to murder the person that's telling you to do that. And so, algebra, we'll see. We're gonna have a very simple way to do the algebra, and we'll talk about that next time. But I'm just gonna leave this here for now. Okay. And so what you saw today was kind of the finite element process. So we went from a system with elements, and so that's kind of like our mesh. Okay. We formed the element stiffness matrices for each of the elements. We assembled them into a single global linear system, and we applied boundary conditions. Okay? And so now we're in a position where we just have to solve the algebra problem. So here is just purely math, and it's math that a computer just happens to be really good at. Okay. And so any questions on any of this? Okay, all right, and so that's it for today. And so on Thursday, we're going to do an example kind of front to back. And so we're going to do kind of this entire process again, but with numbers on Thursday. So you actually get to see that illustrated. And I think that example will be fun because then you can basically see what ANSYS is doing underneath the hood. Okay. And I don't think that example is going to take us the entire time. And so I'm hoping that example will only take about 30 minutes. And then we'll probably spend the rest of the time 45 minutes just kind of working on activity 4, just so I know kind of a lot of people are still working. Okay. And so if you're still struggling with activity 4, make sure you come here on Thursday just so I can help you out. Okay. And so besides that, hope you guys have a good day. Thank you guys for coming, and I'll see you guys on Thursday.
I was looking at it, I'm like, it just started on the side. That looks weird, like the matrix.
Sure. Like that, answers. What is the difference between remote force and force?
That's a good question. So a remote force is basically something that you can apply from a distance. I haven't played around with it too much, and so I only just kind of know the textbook definition, but I almost never use it. So most of the time I just use force. But my understanding is that remote force is like kind of a force that you kind of apply from one part of the structure. I definitely look into it more to give you a better definition, but that's kind of how I understand it. Most of the time I just
Okay.
Yeah. Yeah.
Sorry, I completely forgot what you said like an hour ago. The big one is a constraint.
Big one is the target.
Big one is the target.
The other one's the contact. Yeah. And if you get it wrong, you can always switch it. And so it'll tell you right away. And so it'll say a question mark on it. And so if there's a question mark, you just right click and you say swap the 2, and then it'll. Yeah, so you'll know right away. It's not.
Okay, awesome.
Quick question on 2.4.
Yeah.
When I create the mesh, the top beam on the bridge looks like a cylinder with a bunch of little.
It's just a rendering. So sometimes, ANSYS will take shells and beams sometimes to just render it as if it were a solid element, but it's actually still a shell and beam. So it's just a visual.
Well, my question is that one looks like a cylinder cut up into pieces, but the ones on the bottom, they still look like bricks.
It's because if you remember from the original CAD that beam up top, it actually was a cylindrical one, and the ones on the bottom are rectangular.
Okay.
And so what it's doing is it's just rendering kind of what the cross section would look like just based on what it was before. Because the beam remembers what the cross section is. It's just rendering what that cross section.
Okay, so
It's just a render.
so it's supposed to be different.
Yeah, it's supposed to be.
Okay, I thought it was.
Yeah.
Thanks.
Right, any Charles, Brian, any final questions? Yeah, that's fine. And so for the solid element, you can just run TETs. That's fine. Yeah, that's activity 4 is a challenging geometry. So I'd be surprised if you can do a hex. All right, any guys, any more questions? Okay, all right. So if you have any more, you can email me, but I'll see you guys Thursday.